Hello again. Welcome to another graduate classical mechanics video from Dr. Viv. We'll be discussing the really famous example known as the Focault pendulum. So here's a pendulum. It consists of a bob attached to a string. The Focault pendulum typically that you see in museums have a really big bob, and the string is also very, very long. It's more like something like 10 meters or even 20 meters long, so that this pendulum oscillates almost in one plane. We're going to use that approximation that the oscillation is almost on one plane for the pendulum. Now, the idea is when you oscillate this pendulum for long enough times, the Earth rotates under it. And in fact, when Focault first set up this pendulum in the Paris Fair, I think men and women sort of realized for the first time that the Earth was rotating, because the pendulum never moves away from one plane. So if you find the pendulum actually going from place to place, it is evidence that the Earth is rotating under it. So let's actually figure out the rotation rate of a Focault pendulum. The coordinate system we need is three-dimensional because everything is happening in 3D. So let's look at the appropriate coordinate system. That's your z-axis. X and Y. Let's try to determine what an appropriate coordinate system might be for a three-dimensional vector. Now you can use a coordinate system like the spherical polar coordinates, but it's much more convenient to use a coordinate system that is used a lot in civil engineering, and that's the direction cosines. So the angle A and X axis together constitute a plane. In that plane, the angle alpha is the angle between the shortest angle between A and X. Similarly, the vector A and the y-axis constitute a plane, and in that plane, the angle beta is the shortest angle between the two. And likewise, the angle gamma between the vector A and the z-axis. These are called direction cosines. So we can actually define these angles as follows. Cosine alpha is the x component of the vector A divided by the length of the vector A itself. Similarly, cosine beta is the y component over the length of the vector, and cosine gamma is the z component, az, over the length of the vector A. Using these direction cosines, we can have a much nicer description of the Focault pendulum setup. So let's do the setup as I described it. You have a museum or something. From the ceiling of the museum, you have this pendulum suspended. So that's my x, that's my y, and that's z. So we'll suspend the pendulum from a great height. I'm exaggerating this angle. This angle is actually very small. That's your pendulum. And it's usually got some sort of a spike attached to it, so that around the pendulum in a circle, they arrange little dominoes. So as this pendulum swings, it keeps hitting those dominoes, and you can pretty much see all the dominoes falling after an entire day's worth of rotation. So that's the museum display piece. Gamma is the angle, because the direction cosine with respect to the z-axis is relevant in this drawing. The length of the pendulum will be called script L. That's actually the length distance from where it's pivoted to the center of mass of the bob. So I'm not going to worry too much about the size of the bob here. So this is going to oscillate in a arc-like fashion, the force of gravity is going to be straight down. And that is the only external force in this problem. The force of gravity is the only external force. Well, not quite. There's also tension. The force of tension is another force. Without the force of tension, the force of gravity alone will cause the bob to simply fall down. So the tension and gravity together make this oscillate nicely. Now, I don't know the latitude of the place, but I'm going to assume that the Earth's rotation vector omega is something like that. So if the place has got a latitude lambda, that's my usual symbol for a latitude, the co-latitude is going to be 90 minus lambda. That's this angle here. Co-latitude means 90-degree minus latitude. Co always stands for 90 minus stuff. So lambda is the latitude where the pendulum is displayed. Okay, so this completes our drawing. Now, before we move on to the analysis, let's just project the z component. I'm going to call this value z. All right, now let us write down the tension. The force of tension in vector form is Ft magnitude. What about the direction? It is pointing inwards, so it's going to be negative cosine alpha, negative cosine beta, cosine gamma. Because along the z direction, it is pointing in the positive z direction. Along the x and y direction, it's pointing actually inwards. That's the reason for the negative signs. Now, cosine alpha is just x over L. So what I'm going to do is take L outside because all of these cosines have something over L. And that gives me negative x, negative y. And here, cosine gamma is adjacent, which is this distance. Now, when the pendulum has swung in the lowest position, it's come to the origin. So I forgot to tell you that. My convention is that when the pendulum comes to the lowest point, it is actually hitting the origin. So this is also L. If this is L and this is Z, then this distance must be L minus Z. So cosine of gamma is adjacent over hypotenuse. So it's L minus Z over L. I've already taken the L outside, so that's L minus Z. That's my tension vector. Then there's the gravity vector. That's the other external force. Gravity vector is just 0, 0, negative mg. The force of gravity. And of course, needless to say, the force of gravity is assumed constant in this problem because the pendulum barely deviates from one plane as it's oscillating. Now, in the previous video, which you should look at if you haven't, I derived the equations for the description of motion in a non-inertial reference frame. Those equations are as follows. In the non-inertial frame, which is the frame of the Earth that's rotating, the equations are mr double dot is equal to the external force plus the force known as the Coriolis force, F car, plus the centrifugal force, FCF. So let's write down the terms. The total external force is tension plus the force of gravity. The Coriolis force from the previous video is 2m omega cross v. And the centrifugal force is negative m omega cross r. So that's our master equation. There are two ways to deal with this term. One is to say, we don't like it, I'm going to ignore it. The centrifugal force is going to be really small because it's order omega squared, and the Earth's rotation is once every 86,400 seconds. So this is going to be 2 pi over 86,400. That's going to be another 2 pi over 86,400. It's really, really small. And I think that's as good an argument as anything else. But there's another way to do this, and that is to introduce the concept of the effective gravitational acceleration. So the effective gravitational acceleration, which can be defined as the acceleration due to gravity where it's pointing straight down minus the deflection of the plumb line from the vertical due to the fact that the centrifugal force is throwing out the plumb line a little bit. So if you use a plumb line to determine your true vertical, all the buildings in a certain latitude will be tilted a little bit by this amount. The tilt is extremely small. It's of order omega squared, but this is something that is unfortunately not possible to escape. All buildings of the Earth, all buildings on Earth are tilted. The concept of a true vertical doesn't exist as long as you're using a plumb line to determine the vertical. Because if you use a plumb line, it points in the direction of G effective. The plumb line never points straight into the Earth. The plumb line is flung out a little bit. So when someone tells you that a certain skyscraper is perfectly vertical, you can inform them that if it was used, if a plumb line was used and not some sort of a GPS sensor, then almost certainly the buildings is not perfectly vertical. So you can use the concept of effective gravity and work out this whole problem, but I would rather not do that. I'm just going to ignore that term. So ignoring that term, I get my more simplified equation, mr double dot is equal to ft plus mg minus just the Coriolis term, omega cross v. Okay. Now I can always, while I'm doing this problem, I can always align my omega or the coordinate system. I can always rotate my coordinate system so that the y component of omega is 0. Let's assume I've done that. In fact, as I've drawn it, omega only has z and x components. So I can always arrange to do that. All right. So I'm going to write my omega vector next. In this coordinate system, omega has got a positive value of x. So it's going to be and a positive value of z, and it's going to have no y component. So that's the well, actually, just to be a little more careful, let me draw the Earth itself just to get a better idea of how this omega should look rather than look at my drawing here. My drawing may not be perfectly accurate. So I'm going to look at the Earth itself to get an idea of what the components of omega should be. If this is omega and my coordinate system where the museum is located, that is going to be my z-axis, my x-axis. This is the same coordinate system I used for the Coriolis computation in the previous video. Y-axis into the page, which I've drawn with a dotted line. And my co-latitude, my latitude is lambda, and my co-latitude is 90 minus lambda. That's the North Pole. That's the South Pole. So it is very clear in this drawing that the x-coordinate of omega is actually negative, and the z-coordinate of omega is positive, and the y-coordinate is 0. So my drawing there was slightly flawed. It should look like that in this coordinate system. So this looks better here. So let's follow this one. That's lambda. So this is going to be also, that's going to be 90 minus lambda. So this is going to be lambda. So the x component is negative omega naught cosine lambda. Y component is 0. And the z component is omega naught sine lambda. So that's our omega vector. Finally, the velocity vector of the pendulum bob, well, we don't know what it is, so we'll just call it x dot, y dot, z dot. Where dot denotes time derivatives. Now we have to compute omega cross v. Let's do that next. It's a determinant of the omega components All right, let us proceed to evaluate that. Don't forget that signs have to be assigned to the determinant. Excuse me, that is k hat. So I get I hat times negative omega naught y dot sine lambda minus j hat, because of that minus sign. I have two terms for j hat. I have negative omega naught z dot cosine lambda minus, because of the off diagonal, omega naught x dot sine lambda. And lastly, k hat, that term, negative omega naught y dot cosine lambda. So looking fairly complicated, we may have to make a bunch of assumptions to get ahead in life. Let's put it back in this equation here. So I get m r double dot, which is x double dot, comma, y double dot, comma, z double dot, is equal to F tension, which was right here. So I'll put the tension in first. That's Ft over L, negative x, negative y. It might be useful to see the equations in their full glory before making any further assumptions. And then plus mg, so that's plus 0, 0, negative mg. And then that term. So that's negative 2m times omega cross v, which I have here. So I'm going to write it as ordered pairs, minus omega naught y dot sine lambda. There's a minus of a minus, so that all becomes plus. And the z component is negative omega naught y dot cosine lambda. Okay, so we have actually three equations hiding there. Let's write them out. three equations are the following. Mx double dot is equal to negative ft x over L plus, there's a plus because two negatives make a positive. Well, let me call this equation 1. Then I have the y equation. My double dot equals negative ft y over L minus 2m omega naught is common, so I'll take that out. And then I have z dot cosine lambda plus x dot sine lambda. That's equation 2. And equation 3, mz double dot is equal to, there is a L minus z there. So ft L minus z over L minus mg. And then there's a minus 2m and a minus sign. So the two things cancel out and you get a plus. So I get 2m omega naught y dot cosine lambda. That's equation 3. These are known as coupled ordinary differential equations. In general, they're not easy to solve. I mean, you may have to resort to a computer in order to solve these properly. But we don't want to do that. We know that this pendulum has got some very simple characteristics. So we want to not do the exact thing. We want to do an approximate solution, and we're happy with an approximate answer. So we're going to take the shortcut of working with approximations. This always happens in physics. You get to a certain point, and then you have two options. You can either run to the computer and worship your computer and let it throw up some graphs and say that you've done your day's work, or you can sit around and mess with it, make approximations, and try to get a cute looking answer. We're going to take that approach. So there are many assumptions we can make. First, we're going to assume that the height variation is negligible. And that I've already told you. These Focault pendulums, the ones you find in museums or the ones that you build for your career or science fair or something like that, they're going to have a pendulum length of something like 20 meters. That's around 66 feet. So we're going to assume that L is much bigger than X or Y, which means a couple things. That there's not much Z velocity. As it swings, it's swinging almost in one plane. Z velocity is almost zero. So Z dot and Z double dot, the Z acceleration are both zero. So that's what it buys us. That means that each time I see Z dot, I can neglect it. The other thing we'll use is the small angle approximation. Normally, given how long these strings are, the circle of dominoes that they use is barely about 10 feet in diameter. So that small angle approximation is definitely valid. Small angle gamma allows you to also set Z equal to 0. So that Z quantity, which denotes how high this pendulum swings, is close to 0. So number of things become simplified when you do that. So then I'm going to get the equation that I'm going to work with first is this, because that equation really becomes simplified. So Z double dot is 0. So I'll look at equation 3 first. 0 equals, Z is also 0. So that's just Ft L over L, which is Ft. minus mg, and then that's plus 2m omega naught y dot cosine lambda. The big advantage of using equation 3 is you now have an expression for ft. ft is mg minus 2m omega naught y dot cosine lambda. Well, that's great. We can put that ft in those two equations where ft is present. So let me do that next. Let me look at equation 1 first. Mx double dot is equal to, now when I put ft equals mg minus that in there, with a minus sign up front, I'm going to get negative mg x over L, and then positive, because that minus sign will cancel this minus sign, 2m omega naught y dot cosine lambda, also x over L, should not be forgotten. And then I also have this term all by itself. Okay, now I'm going to do the same thing here. My double dot, this is equation 1 and 2 that we're dealing with next. So my double dot, the same procedure. Except instead of x, I put y. And then this, I neglect z dot because of my assumption that height variation and height velocity and height accelerations are 0. So z dot goes away, and I just have negative 2m omega naught x dot sine lambda. Now remember, we can't make any assumptions about x dot and y dot, because if you say that z dot is 0, the pendulum is pretty much shuttling around in the xy plane. So x dot and y dot are pretty significant. You can't mess with them. So there is still stuff we can do here that makes the problem, even now, this is a little bit better than before. They're still coupled because x double dot has reference to y dot, but it's worse because there it's coupled ODE, but we didn't realize to what extent it was nasty because we didn't have an expression for FT yet. But now we realize it's not only coupled, but it's also nonlinear. It's got terms like xy dot, yy dot, and so on. These nonlinearities make this a very unstable system to solve on the computer, especially for large values of x and y. But we know that x and y are not large. They're going to be really small because of this assumption. So I'm just going to say that these mixed terms are going to be 0 for that reason. Now, whenever I see G over L, I know that G over L is one of my favorite quantities in the physics world because G over L is the frequency squared of a simple pendulum. So omega pendulum squared is G over L. What I mean by that is if I take a simple pendulum and oscillate it, then the angular oscillation frequency of a simple pendulum squared is G over L that you learn in elementary physics. So I can replace G over L by omega p squared. So let me do that. The next thing I can also do, which I should have done long ago, the minute I found an expression for Ft, I should have done it, is to cancel m on both sides. That's Galilean cancellation of the mass for all pendula. Actually, it was not Galileo, but a Greek person called Aristarchus, who first discovered that all pendula swing at the same rate. And he did not take a bunch of different masses and swing it and find the period. No. These were Greeks. You don't want to get your hands dirty. So he gave one of the most brilliant thought experiments of all time. And that is this. Suppose you have a pendulum swinging. Well, suppose you have two pendulums swinging, identical in every respect, side by side. You won't even be able to say the second pendulum is behind the first because they're swinging identical. But when you go and look from this side, you can see both the pendulums swinging side by side. Well, now bring them really close together and spot weld them. When you spot weld them, the two masses are glued, but when you come from this side, you still won't know. And the pendulum will be swinging just the same way. That is his proof that I'm not sure if he used the word spot weld, but that is his proof that the mass does not matter. Totally amazing thought experiment, and it's still the best way to think about why the pendulum's period does not depend on the mass. Okay, once we neglect the nonlinearities, I'm going to get much simpler equation. X double dot equals negative omega p squared times x. And then here, plus 2 omega naught y dot sine lambda. And then from the below equation, I get negative omega p squared y minus 2 omega naught x dot sine lambda. They are still coupled, but now they are linear. These are linear coupled equations. This is linear coupled. That is highly nonlinear. So I'll just put that here. Once you have linear coupled ODE, you have a whole bunch of techniques that people worked out during the days when computers did not exist. So fortunately for us, these techniques are easy to describe. The most famous technique is to introduce complex numbers. The complex numbers are introduced as follows. I'm going to introduce a complex oscillator amplitude, which is x plus iy. In other words, I'm making my xy plane the complex plane. If I have that, then the time derivative of eta is just x dot plus iy dot. And the acceleration eta double dot is x double dot plus I y double dot. Here, I is the square root of -1, the so-called imaginary unit of complex numbers. So now we're going to use this to cast this equation in an interesting way. The way I'm going to work with it is I take the first equation and add it to I times the second equation. Let's do that. So I get x double dot plus I times y double dot. Well, if I do the same thing for this, I'll get negative omega p squared x plus iy. And then here I'll get 2 omega naught sine lambda, which is common to both terms, y dot minus ix dot. Because I'm doing x double dot plus iy double dot. Now, this can be written as follows. I can take a minus sign outside, and I can write this as 2 omega naught sine lambda ix dot minus y dot. But instead of writing minus y dot, I'm going to write this as plus I squared y dot. Why is that? If I is equal to the square root of -1, I squared must be exactly -1. So I'm playing that trick. And now I can write this as negative omega. This is just eta double dot. Eta double dot equals negative omega squared eta minus 2 omega naught. I'll take I outside, sine lambda, and then I have x dot plus iy dot. Well, that's just eta dot. It's a beautiful looking equation which can be solved in a really simple manner. Actually, our friend Euler solved this. So in his honor, we call it Euler's Ansatz. Ansatz is a German word meaning we are trying something. And eta is eta naught e to the zeta t is the Ansatz. where eta naught and zeta are both complex numbers at this point. So let's put Euler's ansatz inside. If you take the first derivative, you're going to get eta naught zeta e to the zeta t. And the second derivative, you need the first derivative there and you need the second derivative here. So I might as well do it right now. That's eta naught zeta squared e to the zeta t. Let's put that into the equation and see what we get. Into this equation, we'll call this equation star. Put in equation star. So I'm going to get zeta squared eta naught e to the zeta t is equal to negative omega p squared eta, which is this, minus 2 omega naught I sine lambda times eta dot, which is that. Observe that e to the zeta t appears in all sides, and e to the zeta t is clearly not 0. If it's 0, then you have what's called a trivial solution. The pendulum is just sitting there doing nothing, and that's not too interesting. So we'll cancel out the trivial solution. And now eta naught also cancels out. Eta naught also cannot be 0, because if it were, again, you'll be led to the trivial solution. And so we have this beautiful equation, zeta squared equals negative omega p squared minus 2 omega naught I sine lambda. That's actually a quadratic equation, sine lambda times zeta. It's a quadratic equation in zeta. Let me write it in a proper quadratic equation form. Bring everything to the left, then I get 2 omega naught I sine lambda zeta plus omega p squared equals 0. Just to make sure that I'm not losing anybody, I'll write the quadratic equation right below here. Ax squared plus bx plus c equal to 0. So here your a is 1, b is 2 omega naught I sine lambda, and c is omega p squared. I always find it beneficial to slow down here because this is such elementary stuff. You learn this in your middle school. You don't want to screw it up in graduate school. So it's always good to slow yourself down when you come to the easy parts to avoid embarrassment. So zeta, we already know secretly. If you don't feel like writing this, you can say it out loud, but secretly we know that x is minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? So that's the quadratic chant, and we have to use that. So zeta equals negative b. That's negative 2 omega naught I sine lambda plus or minus the square root of b squared. Now when I square the I get negative 1. So that becomes negative 4 omega naught squared sine squared lambda minus 4ac. A is just 1 and c is omega p squared divided by 2a, which is just 2. So the 2 can cancel out the 2 here, and the square root of 4 is 2, so that I lose all my 2's and 4's. So I get negative I omega naught sine lambda plus or minus I times the square root of omega naught squared sine squared lambda plus omega p squared. Well, what to do with this? We're going to make yet another assumption, and that is just to neglect. We're going to neglect this quantity, omega naught squared sine squared lambda. Why is that? Why is it important, or warranted rather, to neglect it? So that's the next thing we're going to do, neglect omega naught squared sine squared lambda compared to omega pendulum squared. So let's try to justify it using a numerical argument. Well, the numerical argument goes as follows. Let's find the ratio of omega naught squared to omega p squared. Now, omega naught squared is the pendulum's 1 over the pendulum's period. It's proportional to 1 over the pendulum's period. So this is going to be inversely proportional to Tp over T naught squared. I hope you all remember that omega equals 2 pi by T. Because omega equals 2 pi by T, I can write that. So the 4 pi squared cancel, and I get that. Now, I know by observing the Focault pendulum, in fact, I think I made one as a child for my school fair. So this is going to be a few seconds divided by 86,400 seconds. You see where I'm going with this. A few seconds squared over 86,400 squared is going to be close to 0. So our assumption that omega squared sine squared lambda is of the order 1 or slightly less, not important for this estimate. This estimate is a decent one to have. So we have our new understanding of zeta. Zeta is negative I omega naught sine lambda plus or minus omega p times I omega p. So we can go back to our solution to the Euler ansatz. The Euler ansatz is this answer to our problem. Eta is eta naught e to the zeta t. So that's going to be, now I can write eta naught e to the zeta t as follows. E to the zeta t, I can write eta naught as a plus ib, two complex numbers a and b. So it doesn't really matter for the plus or minus signs. So I'm going to do that. E to the minus I omega naught sine lambda times t is common to both the solutions, so I take it out. And then the plus solution, I'll mate it with a coefficient a, and the minus solution, I'll mate it with coefficient b. Okay, so this is going to be a times e to the I omega pt plus b times e to the minus I omega pt, where a and b are also complex numbers. All right. Having got the solution, this is the answer to the problem. The Focault pendulum is solved. Now it's just a question of checking if this is right or wrong. Let's check the most obvious thing. What if the Earth is not rotating? Non-rotating Earth. In other words, the omega naught is 0. Omega naught is what tracks the Earth's velocity. Omega p is the pendulum's angular frequency. If omega naught is 0, then I get eta. That part becomes 0. So I get eta of t. This non-rotating Earth solution I'll call by the tilde symbol. Eta tilde t is just going to be a e to the I omega pt plus b e to the minus I omega pt. So that's exactly what you expect of simple harmonic oscillations. You get a mixture of sines and cosines. So I can, it's easy to show that this can be written in terms of real, if you want real things, then you can write this as eta t equals some real quantity, a real cosine omega pt plus b real sine omega pt. Or if you want, you can also write this as some overall amplitude c real cosine of omega pt plus some phase factor, which I'll call phi. So this is your standard simple harmonic oscillator. And you expect that because the simple pendulum is a simple harmonic oscillator. But this tells us something important. If this is the non-rotating Earth's component, the only effect that rotating Earth has got is to multiply it by this quantity. So the full solution is got as follows. Eta of t is just equal to e to the minus I some angle theta as a function of time, eta tilde of t. So that's the full solution for the Focault pendulum. Where theta of t is this quantity, omega naught, whatever I wrote there, sine lambda times t. It's a linear function of time. So that's a really interesting solution. It shows you that the effect is actually maximized at the poles. So maximum at lambda equals plus or minus pi over 2. And it's non-existent at the equator. Because equator is theta equals, lambda equals 0. So if you were an equatorial creature, you could possibly never have deduced that the Earth rotated by doing the Focault pendulum experiment. Now there's a very pretty geometric interpretation for this whole thing. And that is this. Let's look at the floor of the museum, which has now become a complex plane. So there's the imaginary and there's the real. So if you plot the eta vector, the eta tilde vector, it's going to be some vector that's going to look like that. All right. And eta of t is got by a simple rotation of this vector by angle theta. So that's our interpretation in the complex plane. So basically, the Focault pendulum is a rotation for the Focault phenomenon. What is it? If you want to describe it, it's a rotation operator acting on the standard solution in the complex plane. So it's a precession of the plane of oscillation. That's all it is. So as time progresses, the plane of oscillation precesses. And so that is a pretty advanced way of looking at this entire problem.